aircraft are designed to cross continents and oceans. Their pilots fly almost entirely by instruments. Yet the radio and navigation equipment on these planes could be disabled by static electricity picked up by the aircraft in flight. This film will give you an understanding of static electricity in aircraft, showing how static electricity originates, the problems it creates in air operations, and how these problems are solved. You're probably familiar with this experiment. As you rub the resinous rod, the rod becomes negatively charged. It absorbs electrons from the felt. The rod then acts as a magnet, repelling other negatively charged articles and attracting positively charged ones. When it is brought into contact with a conductor, repulsion of electrons in the rod forces the negative charge into the conductor. The rod is no longer charged. Here's another example of the effects of static electricity. As he crosses the carpet, this man is being charged with static electricity, just as the rod was by the felt. When he touches the doorknob, the charge leaves his body. The doorknob and metal door are both good conductors. An aircraft, too, acquires and discharges static electricity. It acquires a static charge in one of three ways. Static electricity can be generated by the aircraft's jet engine exhaust stream. Flying through external electrical fields can leave the plane charged. And water or dust particles in the atmosphere coming in contact with the plane can cause static electricity. This third method of charging is known as precipitation static. It is the most common and will be discussed first. This plane is essentially at ground potential. We can assume that it has an equal amount of positive and negative electricity. But in the air, it begins to pick up static electricity. Airborne particles of dust strike the plane. Each time this happens, a positive charge is exchanged for a negative charge. The process is the same as charging a resinous rod with felt. As the plane flies on, it may encounter rain, snow, or ice. The charge is now increasing very rapidly. Precipitation striking non-conducting surfaces charges these surfaces to a relatively high voltage. When it is high enough, a sparking discharge of fairly high voltage occurs from the plastic or glass to the metal body of the aircraft. Such discharges, picked up by an antenna, can produce serious interferences. Meanwhile, the airframe is being steadily charged. The charge continues to build up on the trailing edges of the wings and tail assembly. Finally, the charge overcomes the resistance of the air and begins to escape. As it flows off, the discharge produces a visible corona consisting of very short current pulses. These pulses are picked up by the antenna and greatly lengthened as they are tuned in by the LORAN equipment, radio compass, and radio receiver. Frequencies between 225 and 400 megacycles will be unaffected, but low frequencies, used for long-range transmissions, are often completely blocked out. Flying on through the storm, the plane becomes subject to a different kind of charging. There are sometimes strong electrical fields within a cloud, between two clouds, or between a cloud and the ground. As the aircraft enters the electrical field, it takes the brunt of the electrical force. The aircraft is a better conductor than the air around it. The voltage of the electrical field flows into and through it. As the aircraft leaves the field, the static electricity is discharged into the atmosphere, once again producing a corona. A third means by which an aircraft can acquire static electricity is from its own jet engine exhaust. Exhaust temperatures may separate the heavier positive charges in the exhaust gases and sweep them away. The remaining negative charge builds up, causing an electrical corona. Engine charging is most common while flying at high power at a low altitude. You have seen how an aircraft acquires static electricity and how certain instruments are disabled by the corona discharge. Since there is no way to prevent the plane from picking up static electricity, the solution lies in minimizing the static discharge noise picked up by the antennas. Let's see how this is done. First, it is important that all conducting surfaces be bonded together. If one conducting surface is isolated from another, this will happen. Bonding eliminates this source of static interference. The current now moves smoothly from one section to the other. The problem of canopies, radomes, and other non-conducting surfaces is solved by applying a conductive coating to the surface. The coating drains the charge off to the airframe. There it adds to the currents producing the corona on the wings and tail assembly. The problem is to bleed off the electricity in such a way that it will not be picked up by the antennas. This is done by the use of static dischargers. The static discharger must be able to electrically disconnect the discharge from the airframe and to change the pulsing nature of the discharge. To accomplish this, the discharger is for most of its length semi-conducting. The tip, however, consists of a conducting material. The electric current charges the semi-conducting section to a high voltage and reduces the impulsive nature of the discharge. Simultaneously, the conductor at the tip drains the relatively large current off into the atmosphere. The sharpness of the tip reduces the voltage without impeding the current flow. But as well designed as the discharger is, it must be properly placed to function well. Each discharger must be placed at a point of maximum field strength, but not too close together. This isolated discharger is working well, even though it is not removing all the charge. Another discharger, here, drains some more of the electricity, but the space charge from the second discharger shields the first, interfering with its effectiveness. Placing the second discharger here increases the efficiency of both. On each type of aircraft, the dischargers are placed where they will have the most effect. Now the static electricity is bled off without producing corona or corona noise. When the aircraft lands, any remaining static charge is grounded by conductors in the tires. And the aircraft is now electrically neutral.